In this video, I want to quickly go through the concept of blackbody radiation. So you might be wondering why I have a picture of a rose here. Well, I have a picture of a rose here because I want to talk about something fundamental. So when we look at an object, why do we see it? Why do we see red, for instance, in this case, as the rose? Why do we see rose as red? Well, because rose, the material that makes up rose, absorb all the wavelength or all the green and the blue light, so there's only red light, right? So you're essentially seeing the light as reflecting off of rose, and rose is made of a material that absorb green and blue, so that's why you're seeing red, right? So I just want to get that to start our section on blackbody radiation, and that's also the reason why it's more preferable to wear like light clothing in hot weather, since it will reflect most of the light that falls upon it, and meanwhile a black object absorb most of the visible light they receive. So we can now talk about a concept which is called a blackbody. So a blackbody is an idealized object that absorbs all lights or all radiation that falls upon it, right? So it is I have a picture here of what it looks like, right? So a blackbody absorbs all radiation from all spectrum altogether, right? So that's why hence is black, because it doesn't reflect anything. It absorbs what is coming. It doesn't reflect anything. And then that energy or that radiation it absorbs is emitted through thermal or radiation in this case. So the German physicist Max Planck showed that a blackbody. So first I want to look at these two images of Max Planck. You might have seen these on a meme, of like the guy before he studied physics, after he studied physics, because the left is a picture of Max Planck when he was young, and then the right is a picture of Max Planck when he's older, right, after he started studying physics. So move on to the topic, right? So Max Planck showed that the black body with temperature T emits a continuous spectrum of radiation characterized by the following function. So I'm going to define the following function as the Planck function. So we have two forms. So we'll talk about the first one, which is dependent on the frequency. So the BVT here, right, I have to write a V. V here stands for the frequency. This is going to be equal to 2hv cube c squared, 1 over e to the power of hv kt minus 1. So h here is the Planck constant, k here is the Boltzmann constant, and c here is the speed of light, right? So everything's constant in this equation except the temperature and the frequency, which are the two variables that determines BVT. Then what is BVT? Well, BVT is the intensity of the radiation being emitted by the black body in terms of frequency. That's why I wrote a V here. There's another way to write this, which is write it in terms of wavelength, right? So another formula to write this will be this T should be big T here, because it's not dependent on time, because time is usually written as small t, and big T is usually for temperature. So just gonna correct that real quick. So B lambda here stands for the wavelength, is equal to 2hc squared lambda to the power of 5, and then 1 over e to the power of hc lambda kt minus 1. So what does this tell us? Well, this tells us exactly the same thing as the formula before, right? It tells you the intensity of the radiation with a corresponding temperature, right? So when the temperature is varying, it tells you, okay, if I have a temperature of 6,000 Kelvin, then what is the intensity look like or what is the intensity of the radiation being emitted and by black body, right? That's what it tells you. So as you can see, these two formula really doesn't differ by much, but the second one depends on lambda instead of frequency. So it depends on wavelength instead of frequency, right? So that's the main difference. And to understand this better, I want to show you guys a graph of the following. So as you can see, our y-axis is the intensity, and our x-axis is the wavelength. So what do you see in this graph? So what do you see? Well, the first thing you see is that, well, for different temperature, for 2000 Kelvin, there's a, I'm going to use red pen here. So that's kind of, so for 2000 Kelvin, it goes something like this. For 6000 Kelvin, it goes something like this. And for 12,000 Kelvin, it goes something like this. So what is something you observe? Well, first of all, different temperature has a different curve, if you would like to call it that. Another thing is, I have something here called the lambda max, which is the maximum value of intensity. So for 2000 Kelvin, this tells us that the intensity of maximum wavelength for this temperature, right? So it's right here. And as you can see, as the temperature increases to 6000 Kelvin, it shifts to the left, and then it shifts to the left again, right? So each curve has its maximum intensity at a certain wavelength. So that's going to explain a lot of the phenomena we're gonna talk about. But first of all, I want to talk about the Stefan-Boltzmann law real quick. Just get that before we talk about the lambda max. So Stefan-Boltzmann law. So Stefan-Boltzmann law says it says the flux is equal to sigma times t to the power of 4. So what does this mean? What does the flux in this case mean? Well, it means the total power output per unit area F. So this F here really gives us the total power per unit area F. But basically it's tied to the concept of how much radiation in total is the black body emitting. And you can see sigma here is the constant, so we don't have to worry about that. But the main thing you want to see here is the temperature. That makes sense, right? The hotter the black body is, the more radiation or the more total power output it emits. So you can see that the total power outputs is directly tied to the temperature of the black body itself. And I just want to briefly talk about how we got this formula. We got this formula by integration. We can integrate the flux over the entire electromagnetic spectrum. Because remember, a black body emits radiation in all spectrum, right? It's not that it only, like for example, if I go back to this graph, you can see that for the 6000 Kelvin curves, it emits wavelength. The wavelength is across all spectrum, right? It's not fixed on the visible, because this is the visible right here. So to get the total power output, you simply do an integration over the entire, which actually gives you the area under the curves, right? And then you can actually see here that when the temperature rises from 2000 Kelvin to 6000 Kelvin, right, the area under the curve also increases. So that implies that the total energy output, the power output, also increased too. You can see 12,000 Kelvin has an even bigger area under the curve, right? So that says that as the temperature increases, there's more total power output, which aligns with what we have derived here, right? That the total power output per unit area is directly directly tied to the t to the power 4, right? So now we can move on to talk about what this lambda max means. So lambda max is equals to 2.9290 K centimeter divided by T. So this is called the Wien's law, right? So again, remember, for every temperature, there's a wavelength for which the intensity is at the maximum. So you can see for 6000 Kelvin, the maximum, it's somewhere here, right? So this is within the visible spectrum, and then it shifts toward the left as the temperature increases. So that has a great implication. Like one great example I would like to explain is when a blacksmith put a piece of iron in the fire, right? It first starts glowing red, then as it gets hotter and hotter, it becomes white and even blue, right? So why is that? Well, if you look at the temperature, if you look at the graph here, right? So the general tendency that we see is that as the temperature increases, it shifts towards the entire intensity, or not the entire intensity, well, the maximum wavelength shift to the left, right? So if we follow that logic, you can see here the visible spectrum goes from 400 to 700. So if you just write that down here, right? 400. So 400 will be blue, 700 will be R, right? So the iron initially, as you get it hotter and hotter, its maximum intensity in terms of wavelength is somewhere here. And then as it gets hotter and hotter, it shifts towards the left and becomes somewhat blue. So that's the reason why the iron becomes blue, right? It's because the temperature increase and the intensity at which the maximum wavelength is, right, shift to the left, like similar to this graph. So it went from 700 to 400, or from red to blue. So that's the reason why. And that's also the reason why when a person is lost in the forest, a search can be undertaken using infrared detector, because the body of human temperature is about 37 Celsius, which is hotter than the surrounding nature, which is about 20 Celsius. So that is going to give us a difference in terms of their maximum, intensity, because their peak wavelength is going to be different, right? Our body peak wavelength is going to be different from the environment. Or assuming that you're alive, if you're dead, you still don't cool down. You're same as the environment. That's why they don't use infrared on dead people, because it doesn't really work that way. You're the same temperature as the nature when you die, right? You die and your system no longer works to warm you up, warm the organs, so you just cool down. So that's why the reason this is also the reason why they use infrared for human search, because the human body emits much more infrared radiation than those surrounding as it shifts towards the left. So one example question would be, what if we were to calculate the maximum intensity lambda wavelength for the sun? So we write, okay, mu lambda max for sun, and what I write question mark after. Well, according to the formula, which is 0.290 K centimeter and T, right? So we know the surface of the sun is 5,800 Kelvin. So this is going to be simply 0.290 kcm and then 5,800 Kelvin. So divide. But this is going to give 5 times 10 to the power of negative 5 centimeter, which is 5,000, this unit. So this wavelength lies in the green part of the visible spectrum, right? So what this says is that for the sun, with its surface temperature, its maximum intensity of its wavelength would be at the green part of the visible spectrum. But since the sun also emits a lot of blue, yellow, and red light, our human eye is not equally sensitive to all wavelength. They incorporate all these colors together and see the sun as yellow, but the maximum intensity of the wavelength emitted would be at green. And I want to talk about another topic, which is sort of not related, or sort of related, but it's about the greenhouse effect, right? Well, the average temperature on the Earth's surface is regulated by the amount of energy it receives from the sun, and then the Earth absorbs that energy and then radiate into space, right? And the Earth's atmosphere is transparent to the visible part of the electromagnetic spectrum. So since the temperature at the sun's surface is approximately 5,800 Kelvin, its spectral maximum is in the visible region. So a lot of energy crosses the atmosphere, right? Because its peak emission in terms of its intensity is around in the visible spectrum, and our atmosphere doesn't block that kind of region. So a lot of energy crosses the atmosphere to reach the Earth's surface. So that's the reason why the Earth is warm, right? Compared to some other planets with no atmosphere. So meanwhile, the Earth's surface has an approximate temperature of 290 Kelvin, but it emits mostly infrared radiation. Because remember, for a 290 Kelvin, its graph, if you draw it out, it's gonna peak. Its lambda max is gonna be somewhere in the infrared. However, molecules in our atmosphere, such as H2O and CO2, can absorb that infrared radiation and thus keep some heat in the system, right? So the energy comes into the sun, and then our Earth absorbs that energy and then radiate that energy, and then our atmosphere, the H2O and the CO2, slow down that sort of radiation process, so we can keep some heat in our system. So if it wasn't for the atmosphere, the temperature of our planet would be like more than 30 degrees cooler than it is now. So we're able to live because thanks to the H2O and CO2 in the atmosphere. But unfortunately, human activity, when we burn fossil fuels, that increases the amount of CO2 in our atmosphere. So what does that tell us? Well, if it increased the amount of CO2 in our atmosphere, now there's more heat being trapped before, right? Because imagine the same amount of heat, same amount of energy coming from the sun, but this time Earth is not able to radiate as much energy to outside because there's more CO2 present in the Earth atmosphere because of human activity. Then that's going to increase the temperature of the the entire Earth, right? So this is called a greenhouse effect. Like these gases is going to amplify the opacity of the atmosphere to these infrared radiation that our Earth is slowly radiating. So yeah, it decreased the amount of energy lost to space. So this process is going to lead to a slight increase in Earth's temperature, and this is called a greenhouse effect. And even the relatively small temperature increase are expected to predict to have the important negative ecologically impact. Because for a lot of creatures in the ecosystem, we might not feel it as that way, but for a lot of animals and insects, right? Like, and even a tiny little bit change in temperature, like even a 2 degrees is huge for them. So we really need to. The message I really want to say here at the end is that we need to take better care of the Earth. And remember, this really is a thing that as we burn more fossil fuel, we produce more CO2, which traps more heat inside, and our Earth gets warm up, right? And that will have a huge impact on our environment in terms of ecologically, right, to our surrounding. So that's all I want to say for this video, and thank you for listening.